Problem 2 in the section 5.4 on power in the practice problems was one that we spent a lot of time working on in class, but I wanted to make this video to kind of formalize one of the things that I think is challenging about this problem, and also to try to clarify a couple things that help us approach a problem like this that is a little bit more challenging. So we've got a car, and it's accelerating over a certain amount of time, and it's got a resistive force, and we're asked to find the average power developed by the car's engine. So I copied this problem out of the book, and then I listed the things that we knew, including the final and initial time, the final and initial speed, and the time it took to achieve that speed. And together, those three pieces of information, surely we can calculate an average acceleration over that time period with this information. We have the resistive force. I called that capital F for force, little f for friction. And notice I'm computing the power of the car's engine. And I think that's one of the hard things to understand about this, is that not only does the engine cause this acceleration, it has to overcome the resistive force while it's doing that. So just conceptually, we want to understand that you're going to have to somehow, the engine's going to have to do more work than just accelerating the car. It's going to have to both accelerate the car and overcome this force of friction. So there's a lot of different ways to approach this problem. I want to start by just drawing a diagram. Here's the car. Everything's a rectangle when I draw it. Here we go. That's the car. You want some wheels, we can put some wheels on it. And what we have is there's some force that the engine is applying in this direction. And there's some resistance force, assuming the car is accelerating in this direction. And there's some resistive force, which is our force of friction. So one of the relationships that we have for power is P equals F times V. And we need to acknowledge a few things about this equation that, you might be quick to just say, ooh, we have V. But this V is not a final speed or an initial speed. It's an average speed. Like if you apply a force to and you maintain a certain average speed, like in the elevator problem, then you're going to have a particular power requirement that comes out of that. So I'm going to put an average, a bar over this to indicate that's the average speed. It's not VI and it's not VF. The other thing is that we have to acknowledge is that we're trying to calculate the power of the engine, which means we have to understand or we have to use the force that the engine is applying over this average speed in order to get the power that the engine is applying. So again, we have a force, but it's not the force that goes directly into this equation. If you just took this F and this V, the two non-zero numbers, and then plugged them into this equation, you're not really calculating the power that the engine developed. We got a little more of a challenge to do here. And so let's do a force analysis using the second law. We know that F equals ma. The force equals mass times acceleration, Newton's second law. And that is the net force acting on the object, which results in this particular acceleration. So the net force acting on this object it's the force of the engine moving it forward and causing this forward acceleration. And then we have to subtract off the force of friction. So that's the net force that's actually causing this acceleration. And if I, assuming that this is a constant acceleration, and that's what the assumption, that's a reasonable assumption if we're considering that the car is going from rest to a certain speed. It might be not fully constant over that time, but on average, it's going to be a constant acceleration. And this is a problem where we're dealing with an average. So the force of the engine minus the force of friction is going to be using our equation for average acceleration. We get this. And right away I'm just going to say, well, I know that v sub I is equal to 0. So let me further simplify this relationship. mvf divided by delta t. And remember, what we want in our equation is F sub E, the force of the engine, this thing. So I'm going to get that by itself by adding the force of friction to the other side. mvf over delta t plus the force of friction. And I like this equation as it's written because what it's telling me is that the force the engine exerts is causing this acceleration and additionally overcoming this force of friction. And I can plug this expression in right here. But before I do, let me just figure out what the average speed is. Well, it's pretty easy in this problem. The average speed is just going to be the final speed plus the initial speed divided by 2. That's how you average those two things. And we know again that the initial speed is 0. So v bar, or the average speed, is vf over 2. So let's take this thing and plug them right into this relationship. The power that the engine exerts over this time is going to be the engine force, mvf over delta t, plus the force of friction. That's the total force that the engine is exerting, times vf over 2. And when I actually evaluate this, I'm just going to plug everything in here. I get 1,500 kilograms times the final speed, which is 18.0 meters per second, divided by the change in time, 12.0 seconds, plus the force of friction, 400 newtons. And then I'm multiplying that by another 18 meters per second. It's getting a little crowded over here. And then dividing by 2. So again, I can just plug that whole thing right into my calculator if I'm careful. Let's see. I want the 1,500 times 18 divided by 12 plus 400. Close those parentheses and multiply by 18 divided by 2. And I get 23,850. And according to all these inputs, I've got 3 significant digits. So I'm going to go 23.9. 23,900, and that's watts. 23,900. And let's see, they just said the power. So I could leave it like that, or 23.9 kilowatts is also a fine solution. And that's it. I'm going to do 2 more things in this video, so it's going to get a little bit longer. But just we did arrive at a pretty reasonable solution here. But I want to show a couple of different approaches and how they give the same answer. So instead of using this formula, the power equals the force times the velocity, maybe some of you thought that we would use the other version of this equation. The power of the engine is equal to the work done by the engine divided by the change in time. And that's great. Remember, the work done by the engine is going to be W equals F times D, the force of the engine times the distance over which it did that force. And we got the engine force already. We figured that out right here, right there. That's the force of the engine. So I'm not going to do that again. But then the distance, that this object covers, this car covers in those 18 seconds. Let me just write it here. It's going to be the average speed over that time times the time. In other words, v equals d over t, and I've just rearranged that equation. But again, there's the average speed in my calculation. And if we use our formula for the average speed up here, let's just say v sub f plus v sub I over 2 times delta t. And I just want to show you that on our formula sheet, we have that formula. It's this. Let's take a look. The distance, in this case it says delta x, is equal to half of the sum of the initial and final speeds, that's what this is, times the change in time. So, you know, we can think about the distance conceptually and arrive at this actual equation that we're given on our formula sheet. So, once again, the initial speed is 0, and you see that d equals vf over 2 times delta t. And now if I substitute the distance and the engine force into this equation, I get mvf over delta t plus the force of friction times the distance, which is v sub f delta t divided by 2. And this is our equation for the work. And then notice all we have to do to get power is divide it by delta t. So let me bring that down. The power is going to be this work all divided by delta t. And notice what happens. Let me just rewrite it. This work, mvf over delta t plus the force of friction times vf delta t over 2 all divided by delta t. Well, this delta t cancels with that. And what we're left with is mvf over delta t plus the force of friction times v sub f over 2, which is the same thing we had right up here. So two different approaches to this problem led to ultimately to the same formula. Surely if you plug in the numbers as we did here, you'll get the same thing. And I want to just continue, and I know this video is getting long, but you can turn it off whenever you like. But there's a third way to approach this problem, and it's with the kinetic energy of the car. And so maybe when you first saw this problem, you saw that we have these different speeds, we have a mass, those together are used to calculate kinetic energy. So let's see what that looks like. I think it's a little more of a stretch to get there, but it works. And I'm going to start with this formula again, knowing that the work the engine does divided by the time that it does that work is going to be equal to the power that the engine puts out. And now we are going to deviate from our formula. You have a formula on the sheet. It's kind of an unfortunate formula. It says that the work is equal to the change in kinetic energy. And ultimately, it's true. Work does cause a change in kinetic energy. But the work the engine does is responsible for the change in kinetic energy of the car. But we also have to do the work to overcome friction. And so really the work that the engine does is the combination of these two things. And you got to think about it from an energy standpoint and conceptually, like the same thing we were doing with the force over here. The engine force is going to cause acceleration and additionally have to overcome the force of friction. That's what this is doing too. This is this work that is being done results in an increased speed of the car plus the work done against friction. So let's expand that a little bit. it's going to be the final kinetic energy minus the initial kinetic energy plus the work done against friction. And again, this is just 0 because the initial speed is 0. So I get the work that the engine does is 1/2 mv final squared, the final kinetic energy of the car, plus the work done against the force of friction, which is F sub F times D. So if you go back, we know what D is. It's here. And we know everything else in that equation. So let me just copy that equation for D over here. We got D is equal to the final speed over 2. It's really, that's the average speed is what that is, times the change in time. And so now I've got my power equation, I've got my work equation all done, and I got my distance here that's going to substitute right in there. So let's put it all together, and we get P sub E, the power of the engine, is equal to 1/2 mvf squared plus F sub F, the force of friction, times Vf divided by 2 times delta T, all divided by delta T. And that second delta T on the bottom, it comes from our power equation. So let's do a little bit of algebra here. Notice on the top, there's 2 terms. There's this term, and then we're adding in this term. And they have a couple of common factors. They both have a half, and they both have a V sub F. This one has a V sub F squared, but if I factor that out, it might look something like this. M V sub F plus F sub F times delta T. And I'm going to multiply all of that by V sub F over 2. So what I've done is I've factored a V sub F over 2 out of this term, just leaving these guys behind. And if I factor a V sub F over 2 out of this term, I leave the MVF behind. And then I'm dividing the whole thing by delta T. And one way, I could just put this delta T over here underneath right here. But if I actually divide it into these parentheses, I'm going to divide each of these terms by delta T, and I get MVF over delta T plus F sub F times V sub F over 2. And again, that is the same formula that we had right over here. Exactly the same. And it's also the formula we had here. So again, we have this formula sheet. It's got all these formulas on it. And I find this to be helpful in some respects, but it's also like more formulas than we actually need, because you see, they're all the same. This formula for power is really just a combination of this formula for power right here, and then this formula for work. And so regardless of how we approach this problem, we end up with the same answer.